Now, when we want to characterize the susceptibility of different kind of magnetic material, we want to distinguish them on the basis of how do they react against magnetic field and how they react to a difference in temperatures. Now, for a paramagnetic substance, this thing can be relatively straightforward-ish. So if you have your susceptibility, you can correlate it with temperature for a series of constants, but we know it's inversely proportional. So this is a series of constant inside of the material, but it will go like 1 over t. This series of constants can be collated all together to give you something that ends up looking like this. So the susceptibility is inversely proportional to temperature. This thing is called the Curie constant, and this thing as a whole is called the Curie law. So when we want to look at a paramagnetic behavior, a paramagnet and its susceptibility will follow an inverse proportionality behavior with temperature. So if your thing is paramagnetic, it will have completely randomized magnetic moment inside. Overall magnetization is 0, but the reaction with temperature will follow the fact that as you increase the temperature, the susceptibility decreases. If you want to do some mathematic tricks here, you could do the inverse of the susceptibility. So if you were to plot chi to the minus 1, so it's 1 over chi, will be linear with temperature, which can also be nice to do. This basically comes from the fact that the alignment against the magnetic field, which is small and local, is only made more difficult with increased temperature. So when you go very much higher, then the susceptibility will decrease. Now this is supposed to be valid from 0 Kelvin to infinity, but this is only valid for a very specific case, which is the case of a perfect paramagnet. If your paramagnet is not perfect, it means that adjacent unpaired electrons and the magnetic moments of adjacent atoms will not be independent of each other. So in a perfect paramagnet, you have complete independence of anything that is side by side. They can just go and orient themselves in whichever way from 0 to infinity Kelvin. But in a non-perfect paramagnet, at some point you might get effect of interactions, and the effect of interactions will add themselves on top. So when you have interaction between adjacent magnetic atoms, meaning adjacent magnetic moment, there is a deviation from the perfect inverse relationship of the Curie law. So this thing is called the Curie-Weiss law, in which this is the Curie constant and this is the Weiss constant. So your susceptibility, instead of being perfectly inversely proportional to temperature, has a correction point. So this thing just shifts your thing. And the type of paramagnetic substances have a slightly different behavior as they go to a point of interaction. So what does this mean? This means that you have a perfect paramagnetic behavior, which is your normal Curie law, and then you, depending on the value of your theta, you can shift your Curie law in one direction or the other. Note that the plot here is in susceptibility to the -1, so we can have the linearity with temperature. The slope in this plot is the Curie constant, and then you have the correction to the temperature given by the Weiss constant. So if the susceptibility that you measure is higher than the one of a perfect paramagnet, it means that your material has a tendency towards towards ferromagnetism, meaning that it likes to start to orient the magnetic moments all in the same direction. If your susceptibility is lower than the one that you will measure in a perfect paramagnet, then you have a tendency towards anti-ferromagnetism, meaning that the magnetic moments will start to shift to go in anti-parallel arrangement to each other. You can shift from one point to another, but the Curie law and the Curie-Weiss law are just for the paramagnetic regime. So how does this thing actually look? When you have something with ferromagnetic ordering happening, you have a higher susceptibility than normal when your substance is paramagnetic, because there is a local interaction of your spins. When the Weiss temperature is higher than 0, the susceptibility tends this tends to 0, this tends to infinity, and the inverse of the susceptibility will tend to 0. So the closer you go to 0C, the more at some point will go to an asymptotic behavior. And at the interchange moment, so when the temperature is very much higher than this thing that we call the Curie temperature, you can just follow this behavior like this. The issue is that when you go close to the Curie temperature, things might actually change, and whatever you measure here depends on the material. There is the interchange point in which what happens inside of the material is that you have a magnetic transition. So from disordered moment, completely randomized from each other, you end up in ordered form, in which the moments are aligned in the same direction in comparison to each other. So regardless of the direction, they go all in that way. So this means that in a ferromagnet, your theta, we call it the Curie temperature. The Curie temperature is the temperature of ferromagnetic ordering. The process is spontaneous. It just happens because you're cooling the material. Regardless, depending on what material do you have, the temperature is different, but the behavior is always the same. So you're cooling it. At some point, the atoms will start to interact so much that they will lock into the alignment position. This will be your ferromagnetic ordering temperature. If you heat back up and you go above the Curie temperature, you will disorder the atoms, and more than the atoms, you will disorder the magnetic moments, and your substance will go back at being paramagnetic. It's perfectly reversible, just a function of temperature. And how does this look, experimentally speaking? If you try to do a measure of susceptibility of a material with ferromagnetic behavior, you start at paramagnetic, which is the higher temperature state. You follow this thing, as you can see that it's going exactly as we were saying here, but as it starts to go close to the Curie temperature, the asymptotic behavior stops. You cannot see it fully, and it just shifts into something else, and it goes to a plateau. You can see that here the researchers have indicated the TC 250 Kelvin, and they plotted, so the inset of this plot is the inverse of the susceptibility, which is very nice because it means that you can fit this law as a straight line passing through the points. Your 250 is the point where the Curie-Weiss starts to deviate from linearity. So whatever is here is not a paramagnet, but this gives you the power to figure out where is your magnetic transition. The fact that you can go back and forth and back and forth and back and forth as a function of temperature is something that is experimentally nice and proved. And we can see it fully oops, if I can make this thing behave, otherwise we will see it in another occasion, because it doesn't seem to like me in this moment, even though I tested it earlier. No, he really doesn't like me. Okay, so just didn't like my laser pointer, it liked me good enough. So this thing is a video that shows the Curie point of iron, because iron is a ferromagnetic substance. Now the trick is that iron has an incredibly high ferromagnetic transition temperature. So you must go to very high temperature to be able to see your iron going off from ferromagnetic behavior. So if your iron is ferromagnetic, this is an iron bolt here. If your iron is ferromagnetic and there is a magnetic field, your iron is attracted by the magnetic field because it densifies the lines of force and it just goes there. This is room temperature, but what this guy is doing is flame throwing here with an oxygen flame, able to go to very high temperature, and heating up the material. You can see that it starts glowing because it gets very, very hot, but you can also see that it starts shifting. So as you increase the temperature, the attraction that your material is feeling against the magnetic field disappears. So when you get above the Curie temperature, your material is behaving like a paramagnet. But as it cools down in air, it goes back to being attracted by the magnetic field. So the magnetic field there is not changing because nothing is changing there. But your substance, as yet heated, it loses the ferromagnetism. If it loses the ferromagnetism, it's not attracted to the magnetic field anymore, and it can just jump around freely. If it cools down again and it goes below the Curie temperature, it starts to behave like a paramagnet once again. So now if I go back to my flashy laser pointer and we try to go on, we have another option of ferromagnetic behavior, which is antiferromagnetic ordering. An antiferromagnetic substance will get towards a state that has a lower susceptibility than a normal, fully disordered paramagnetic regime. Because fully disordered means that statistically speaking, you could have some order, some anti-alignment order. This thing really wants to go into full anti-alignment. So we have another correction of the Curie-Weiss law in which theta gets called Tn, which is the Néel temperature. When you are below the Néel temperature, you tend to infinity with the susceptibility, so the inverse of the susceptibility will tend to 0. But this thing can actually go below 0, which a normal Curie temperature cannot do, because that's not allowed. So this is the temperature that gives the transition between a fully disordered to a completely antiferromagnetically ordered. Now the Néel temperature needs to be higher than 0, but by nature of going through the law, so just mathematically speaking, the final point of interpolation of this line can actually go in negative. So the Weiss constant of an antiferromagnet can be negative, depending on how strong the antiferromagnetism is and how low the transition point is. So you follow, when your substance is paramagnetic, you can follow the Curie law with this correction, but the correction depends on this parameter that can be even lower than 0, and your substance will diverge to a lower state of susceptibility at a certain point that we call the Néel temperature of antiferromagnetic transition. So in a real material, you can see here that is split in two different plots. So this plot is plotting you the susceptibility as a function of temperature. The second y-axis is the one with the inverse of the susceptibility, so it's two plots in one. So following the susceptibility as a function of temperature, you cool down, this thing starts to increase, we are following this curve, but no, we get to a transition point and your susceptibility drops brutally. What you can do on the other way is your susceptibility is supposed to be linear. The inverse of the susceptibility is linear with temperature. So you can see that there is a straight line cooling down, but then there is this bump at the end. So this point that you see over here is your Néel temperature of transition. If you want to continue interpolating the line, you can see here that you end up at negative temperature. And that negative point is your Weiss constant. So that Weiss constant cannot be physically measured. It can be extrapolated from the susceptibility that you measure, because it can be a temperature lower than 0 Kelvin. So the antiferromagnetic region is the region between 0 Kelvin and the Néel temperature of ordering. In this region, the susceptibility increases as a function of temperature, which you can see here. When you go to the shift point, your material goes from antiferromagnetic to paramagnetic, and then it starts to decrease as the function of temperature. Now, this was the temperature dependency. You can also have dependency as a function of field. So in an antiferromagnet, when you cross the Curie temperature, if you do it under magnetic field or if you do it away from a magnetic field, it does make a difference. Because if you pass your Curie temperature and you're already aligned in magnetic field, you have a greater amount of magnetic moments that will actually go in that direction. This is the reason why when you do measurements of susceptibility, you want to know what is the zero field cooled behavior. So if you cool in zero field, there is no magnetic external force that is giving a pre-alignment to your moment. You still go to the Curie temperature of transition and you just chill around like this. It's fine. But then if you heat it back up and you put the field on, so it's the same material, it should be able to go back and forth and end up in the same susceptibility. But when you cool down in field, so you impose a magnetic field when your material is in paramagnetic state, when you cool, you start to see that yes, the transition temperature is still the same, but there is a gap between the zero field cooled and the field cooled line, because when you go into field cool, more moments align in the direction of the field, so the susceptibility of your material immediately becomes higher. This is the experimental susceptibility of a calcium ferrite material. When you do it with an antiferromagnet, instead, there is zero reason why having field cooled or zero field cooled will make any difference, because the material is anti-aligned, so it doesn't matter how much field you put on, there will always be an anti-alignment that cancels out the internal magnetic moment. So there is literally no reason to see a difference, and that's exactly what happens. That when you measure your susceptibility, once again, mind the double plot of susceptibility as a function of temperature and inverse of the susceptibility. If you cool down in no magnetic field, you can vaguely see the yellow pointers underneath. You cool, you go through the Néel temperature, your susceptibility drops. Nice. You heat back up, you cool in magnetic field, there is exactly the same behavior. It does not make any difference. So if you are ever in doubt of is my material a ferromagnet or an antiferromagnet or what is going on here, you can just look at these curves. for an antiferromagnet, you expect that the susceptibility will drop under the temperature of ordering and will be overlapping when you try to put field on. For a ferromagnet, the susceptibility rises as like below the temperature of ordering, and it can be further increased, so you will have a split of the two curves if you cool in zero field or with field. So this is a very interesting behavior, and this behavior actually builds down and cools down and boils to the fact that you have magnetic domains in the material. Once again, this is a business that can only ever happen at the solid state, because we're not looking at individual atoms, we are looking at the whole material and its reaction against the magnetic field. So there is a series of interacting atoms, and you have a very big material. You saw the video before. There is a whole bolt of iron. That whole bolt of iron is ferromagnetic. Can you imagine that that thing is just a full block of material with no internal area? It doesn't really sound good, and that's the concept of magnetic domains. So when you have a ferromagnetic material that has gone below the magnetic ordering, you just have a series of regions in the material in which the spins are the magnetic moments of the atoms are aligned with each other. And this is a behavior of the material. So in any region you look at in the material, you will find magnetic moments aligned with each other. But in an unperturbed state, so if you just make the material go through the Curie temperature, the overall material will try to minimize this effect, because this is an energetic effect. There are a lot of magnetic moments interacting with each other. So they will try to arrange after the spontaneous alignment, upon spontaneous alignment, in a way that minimizes whatever comes out. So even though the material is ferromagnetic, the overall magnetic moment tends to be towards zero, because the local area alignment negates the field. It just goes back to zero, because you have this that goes in this direction, this one that goes in this direction, this one that goes in this direction. The overall is zero. If you magnetize, so if you apply a field and you encourage your material to follow the field, you harvest the fact that your material likes to accompany the magnetic field even in paramagnetic state. As you go through the Curie temperature, you go through a Curie temperature with a sort of pre-alignment of all the regions in your material. So not only you have a series of regions in your material of coherence of the magnetic field, but all of these regions are aligned together with the external magnetic field. Now this material has an overall magnetic moment. This effect is the effect that gives you the split in the zero field cooled magnetic line, and it's also the effect of magnetization of the material. The total magnetization is different from zero, and is the reason why against magnetic field a ferromagnetic material will have a delay of the reaction. This delay is called the hysteresis curve. So given the fact that you have these moments that are ordered, and you can align them with field, and you can try to switch them with field, you have a sample history. So your material has a magnetic memory in itself. Since it's ferromagnetic, it's below its Curie temperature, you have this alignment. But if you start to align all the region in the material in one direction, they will go to a certain energetic state. Trying to switch them will encounter a certain resistance, and this thing is the thing that creates the hysteresis curve of the material. An hysteresis curve fundamentally looks like this. So you have the magnetizing force, so how much magnetic field do you impose, and the flux density. This is the same thing that we were seeing before. So you have applied and the lines of field inside. If you have your material that just went through the Curie temperature by itself, but with no perturbation, you have the zero net magnetization of the material. So there is no real, if you didn't put any magnetized force, there is no flux in the material. The material is nullifying its own magnetic moment in alignment to stay chill and nice. If you start to increase the magnetic field that you put in your material, the moments in the various magnetic domain will start to all align in the same direction until you get to a saturation point. So when all the magnetic domains are completely aligned, you are in saturation behavior. Now let's say that you switch off the field, just reduce it. Your material that preserves this magnetic memory, because now that all the domains are aligned, they want to stay aligned, they will tend to stay aligned, goes to a remanent alignment, a remanent magnetization inside, so a flux density inside that is way different from zero. So even a zero field, after you put your material into saturation behavior, you have these remanents. If you now try to switch the field in the equal and opposite direction, your material does not go back to zero, it goes down into this curve. So you need to put an additional level of effort in order to bring the material back to zero magnetization. So it's not that you switch off the field and you drop the magnetization, you switch off the field and you have a certain coercivity that shifts the reaction. So how much effort do you have to put in terms of magnetizing force for your material to go back to no magnetization? If you keep increasing the field, though, the only thing that you're doing after having put the material back into zero magnetization is shifting the orientation of all the magnetic domain into an opposite direction, so an opposite saturation. So still saturated, just if it was saturated like this before, now it's saturated like this. Again, if you switch it off, you go back to the remanents in the other direction. And if you try to bring your material back to zero, you need to apply an additional magnetizing force. You can notice that in no occasion after the original magnetization, you pass back from the 0 point in a normal ferromagnetic hysteresis behavior. So this is the summary of all these steps that we did. If your Curie temperature, if your measurement is known below the Curie temperature, there is no way your material can pass back to the 0 point. This is something that we can actually see as an effect, and it makes the difference between a magnetic material and a magnet. A magnetic material is a material with unpaired electrons in the valence shell, and as such with magnetic moments available. A magnet is something that can actually have magnetization inside of the material. So you need to be at this point, not this one. And this is the example, for instance, of steel. So steel is an alloy, 99% of iron, 1% of carbon. So easily you can imagine that this thing will have plenty of magnetic moments to go around, and we'll be able to use them for some purpose. The Curie temperature of steel is incredibly high, so it's 700 plus, so it's almost 800 degrees Celsius. So you really need to heat steel a lot to bring it into paramagnetic behavior. So something like this, which is steel scissors, by itself, by its nature, is a magnetic material. This is a material that is below its ferromagnetic ordering. This doesn't make it magnetic, it just makes it ferromagnetic, meaning that the moment inside of these things are ordered. But if we want to make it magnetic, so something that will retain a flux inside, you need to go through the hysteresis loop. So you need to bring it to saturation magnetization, and if you remove the magnetic field, this will keep a remanence. So how can we prove this thing? We can absolutely prove the thing. So what we need to do the trial of this thing is something metallic, like a pin, and what you expect is a magnetic material will attract a metal. This is what we know from ancient Greece. But if your material is simply a ferromagnet but is not magnetized, you can see that it doesn't matter. Like, I can shake it, but I cannot attract it. I'm not attracting my pin. So this steel that you can see is ferromagnetic in its nature, is not magnetized. So to magnetize it, we actually have to use a permanent magnet. So if I have my magnets over here, so this is a magnet in itself. I could hang it on my whiteboard. So you've seen plenty of this. We have them in the tutorial downstairs. So this thing can actually enforce magnetism. So if I take my steel scissors and I put the magnet, you can see that this does what you expect. But this is me pushing the tip of this steel scissors into a nice magnetized state. So I'm imposing H, and I assume that by imposing H, I will just bring all the magnetic domains in alignment with the magnetic field. Now that the magnetic domains are in alignment with the magnetic steel, my pin down here, can you see that now is moving to follow? And now my steel is actually magnetized, because even with no additional magnetic field added, I have the remanence flux given by the alignment of all my magnetic domain inside of the material. So this is the proof of the hysteresis behavior. These scissors, now that I magnetized the tip of it, they will never go back to a zero magnetization point unless I give them an incredible amount of time, or I heat them up above the Curie temperature. So this is the proof that we can actually do this game of hysteresis. Based on this game of hysteresis and this game of actual constant magnetic behavior, we are going to move into the real application of magnets and what you can expect of magnets as you think of them in the final video.